Hi folks, Chris McClure. Now we're going to continue this discussion about estimating a population parameter. We've already talked about the proportion and the mean in section 7.2 and 7.3. Now we'll address the standard deviation and variance. All right, same idea as we already talked about before, in that we use a point estimate plus or minus a margin of error, but we will talk about that margin of error shortly. Now, last time we talked about the t-distribution. That was brand new to you probably. We're going to talk now about a brand new distribution yet again. It's called the chi-square distribution, that we will use to construct confidence interval estimates of a population, standard deviation, or a variance. We'll also talk briefly about determining sample size required to estimate a population, standard deviation, or variance. Chi-square distribution. Okay? In a normally distributed population with a variance sigma squared, I'm going to go back and emphasize the fact that this is only for normally distributed populations. We're going to assume that we randomly select independent samples of size n, and for each sample compute the sample variance s squared, which is the square of the sample standard deviation s. The sample statistic chi-square has a sampling distribution called the chi-square distribution. Okay? Here's the calculation, where you take sample size n minus 1 times the sample variance, which is s squared, divided by sigma squared. Okay, sigma squared is something that you may not exactly know, but you might be told in a problem or assume. Okay. Now, if you were to graph the chi-square distribution, you would see that it is symmetric. It's not symmetric, it's skewed. And all chi-square random variable values are non-negative. They're always positive or zero. And there's a different chi-square distribution for a different value for n. Sample size minus 1 is going to be the degrees of freedom. So different degrees of freedom will give you a different shape of the chi-square distribution. Here we've got a smaller degrees of freedom for the chi-square distribution that you see in blue, the larger degrees of freedom in red for the chi-square, and the larger the degrees of freedom, the lower the peak is and the further to the right is. As a matter of fact, the degrees of freedom is going to exactly equal be where the peak is. That's going to be where the mode is. Okay? Values of chi-square can be 0 or positive and never negative. Chi-square distribution is different for each number of degrees of freedom, which is n minus 1. I'm going to show you the table. I'm going to pull out my table here. If you look in the right after the t table, we talked about the t table last time. Well, right after the t table, you'll see the chi-square table, table A-4 in the textbook. There are also chi-square distribution tables on the internet too. And also down the left-hand column, you'll see the degrees of freedom, and across the top we have these column labels: area to the right of the critical value. Keep that in mind. It's area to the right, not to the left, but to the right. Okay. So we're going to look at an example here. Simple random sample of 22 IQ scores. Sample size 22. IQ scores is obtained. Construct a confidence interval for the population standard deviation sigma. requires the left and right critical values of sigma, corresponding to a confidence level of 95% and a sample size of n equals 22. We will find the critical chi-square values corresponding to a 95% level of confidence. Now, here's how we can get those critical values for chi-square. So here's a generic chi-square curve here, and we want to find this critical value that's associated with 0.025 in the left tail and 0.025 in the right tail. Note that the chi-square distribution graph is not symmetric. So we're going to have to actually look up two different numbers. Now, this is for degrees of freedom of 21. 22 was our sample size. Minus 1 is 21. So let's go back to our table. So there's our table, chi-square. And we will go down to 21 in the left column. And to get the left critical value, now let's stop and think about this. We want a 95% confidence interval. That means alpha is equal to 0.05. Half of 0.05 is 0.025. So that means that we need 0.975 to the right of our left critical value. So for 21 degrees of freedom, we're going to go over to 0.975 column here, and we're going to get a critical value of 10.283. And indeed, there's 10.283 for this left critical value. And to get our right critical value, we have 0.025 area under the curve to the right. So we'll go down this column, third from the right, and down to the degrees of freedom row of 21. And we will extract 35.479 as our right critical value. So I just showed you how to get your left and right critical values for chi-square. We're going to use S squared as the best point estimate of the population variance because it's an unbiased estimator. And by the way, sample standard deviation is a commonly used point estimate of sigma, but it's not necessarily the world's best, but it's easy to use and it's commonly used, but it's not an unbiased estimator. You would think that it is because of the fact that S squared is an unbiased estimator of sigma squared, but S is not an unbiased estimator of sigma. Here's our cast of characters here. So you know what sigma is. It's the population standard deviation. Sigma squared, variance, S, and S squared, N, E. We're still calling E the margin of error. And then chi-squared L is the left critical value. And chi-squared R is the right tail critical value. Again, we need a simple random sample, and we must be sampling from a normal distribution, as in a normally distributed population. And actually, this is how you construct your confidence interval for sigma. You're going to, in the numerator, take n minus 1 times S squared for both the left and right limits. But in the left limit, you're going to divide by chi-square sub r. In the right limit, you're going to divide by chi-square sub l, which you saw how to extract those values from the table. And if you need a confidence interval for sigma, standard deviation, then just take square roots throughout. Okay, so let's tick through the list. We verified our assumptions. We used our table to find critical values. And then we evaluate the left and right limits. both for sigma or sigma squared, depending on if you want standard deviation or variance, and use appropriate rounding when you express your final answer. Confidence intervals could be used informally to compare the variation in different data sets, but the overlapping of confidence intervals should not be used for making formal and final conclusions about the equality of variances or standard deviations. I think we've mentioned that before. Going back to our example where we have a sample of size 22, took part of a study. Subjects had a standard deviation IQ score of 14.3. So we're going to construct a 95% confidence interval estimate of sigma, the standard deviation of the population from which the sample was obtained. Now, if you were to plot a histogram of our sample, which you don't see what our sample is, but this is what the histogram looks like. It's roughly bell-shaped. And if we really wanted to, we can construct a QQ plot to verify that our data are normal enough, okay, that we've at least have some convincing evidence that we've sampled from a normally distributed population. Okay. So, now we can go ahead and construct our left and right limits for our confidence interval. First of all, 21 is our degrees of freedom. So that's what we're going to put here and there. Our S squared, our sample variance, is going to be the square of the standard deviation. So in our calculation for this problem, we were told that the standard deviation is 14.3. So we will square that to get S squared, both for the left and right limits. Now, we had already found our right critical value, 35.479. We'll put that in the denominator for the left limit, and likewise we'll put in chi-square sub L for the denominator in our in our right limit that you see here. And then go ahead and evaluate both of these left and right limit expressions, and you can round just to 1 decimal place. If you want to get a confidence interval for sigma squared, then you'll just leave it like you see here. But if you want a confidence interval for just sigma, the population standard deviation, then you'll take square roots of both the left and right limits. Okay, and we have 95% confidence that the true population standard deviation is contained within this interval. All right, so that's a pretty straightforward calculation to get your confidence interval. Now, to figure out what sample size that you need for a certain percent deviation, then we're not going to get very much based on the software that we have. But there's a table, though, and you'll see this toward the end of section 7.4. Okay? And you should be using this, and when you take your final exam, I will provide this to you. Now, there's 2 columns and 2 rows for this. This first column, left-hand column, is for sigma, and the right column is for sigma squared. The first row is for 95% confidence interval. The second column is for 99% confidence intervals. I'm pretty sure that you will not be asked to calculate sample sizes for any other percent confidence other than 95% or 99%. And how this goes is that if you want to know what sample size that you should use so that you could be, say, for example, 95% confident that your standard deviation is within, say, 5% of sigma. Then you would just look to the right and you pick out 768 as your sample size. Or if you want to be 99% confident that your variance is within, say, 20% of the true population variance, then you should use a sample size of 369. That's how that goes. So if we want to estimate the standard deviation sigma of all voltage levels in a home, we want to be 95% confident that our estimate is within 20% of the true value of sigma. True value of sigma. So, sorry about that. 95% for sigma. So we'll use this quadrant up here, 20% deviation, and we'll pick out a sample size of 40. Okay, so that's how you read the table. That's just a real quick, easy example. So that's it now for doing estimation of population variances and standard deviation. Okay, so that's it for recording for today. And I will record some videos for Chapter 8 tomorrow, Tuesday, okay? And then I'm going to be out of town, like I said, for about a week. Yeah, and you're going to have some limited contact with me on Wednesday this week, and then maybe Monday and Tuesday of next week. But for pretty much all of Thursday, Friday, Saturday, and Sunday, I'm going to be out of the loop. Okay, I'll send an email to discuss that further. All right, have a good day, folks. I'll see you next time.